I can start the recording, but anyhow, I'm not I'm not starting the class, but just having some discussion. That's all. So today we have this topic. This is will about the dynamics of the power system, and we have already covered the now. That means what is stability, then introduction, and then wide area monitoring of, and then the different tools which we have it for monitoring. It's basically related to the stability monitoring. And did you refer this book here? Did you find it?
A book?
Yeah. Yes, it will be required. It will be required. Both books will be required for your study.
I think I had it here, but I don't remember where it was.
Because most of the contents will be from this book.
Yeah, I have this. The Kunder book, right?
Yeah,
For
it's a
system
Kundar
stability.
book.
It's part 1, part 2. Yeah.
Is it in 2 parts?
Yeah, I got it in 2 parts. But...
Okay. But it's only one complete. I'm not sure. Because the hard copy that is in the full one book actually.
Of course, the hard copy is going to be one book, but here I'm talking about the soft copy again.
Okay. Then because this book is also a good one, and because many of you do not have much background about the power system, then I would suggest that to go through this book also, right? Because some of the topics from this book, they are for undergraduate level also. So those who do not have sufficient background about the electrical power system, then they can refer this book. That will be more useful. And once you have read this book, then you can start with the Kundar book. That I can say. Right. And again, this book by Hadi Sadat, it also has some examples with the use of MATLAB. So because once you know MATLAB and then how to solve some number problems in the MATLAB software, so this could be good starting if we refer this one. Right. Okay. Should we start or we wait for a few more minutes? Yes, please.
Yeah.
Okay then. So today we have the topic, it is on power system dynamic analysis, and mainly we will cover this analysis on single machine infinite bus system. So it means normally you have a large power network and you have several generators and then the lines, but our analysis will be mainly focused to a one generator, and then connected through a line to a large power network. So that means we will consider the dynamic analysis of one generator with respect to a large network. We will not consider the dynamic analysis of several generators in the system. Right, so we will just focus on one generator with respect to the complete network that way. So what we have here, because at the end of the topic, you should be able to model a small signal model of single machine infinite bus. SMIB stand for single machine infinite bus here, this one. And then have some analysis, a small signal analysis on SMIB. And for this, we will have some examples, and it will be from the book by Hadi Sadat and using the MATLAB software. So we will do some examples given in the Hadi Sadat book and even the Kundur book, right? You will have an understanding about what parameters, how they influence their system stability. And then the effect of PSS on stabilization, because the last discussion what we had, it was about the stability, power system stability. So how does the mainly when it power system stabilizer, it is mainly for rotor angle stability to damp out the rotor angle oscillation. So this one is this here we refer to the stabilization in respect of rotor angle stability. If you look at the power system dynamics, it in fact I will show in the next slide that the system response of a power network, or including the components, everything, it is in a wide range of time duration scale, I'm saying. And so the power system here, we want to know how the power network will respond whenever there is a load change, or maybe some kind of severe disturbances, like you trip one of the line or generator, or else there is some short circuit fault here. So that means we want to understand how your power network, right, how your power network will respond, what will the dynamic variation of frequency signal, what is the dynamic variation, how the voltage will change, how the current will change, how the frequency will change, or rotor angle will change whenever you have these disturbances, either load disturbances or some severe disturbances, like the tripping of the lines or generators or the short circuit here. In our power network, remember, in our power network, all the components, they have their own dynamics here, right? And against this disturbance, because if I say, for example, your turbine, your generator, and then again, even your transformer, though with the transformer, it is static device, all right, because in transformer, you don't have any rotating component. Generator transformer has a rotating component. Uh, Transformer is just simply a static one, static device. Line, transmission line, again, it is a static. You don't have anything dynamically varying. But thus the components here, they have their own individual dynamic representation. Turbines, generators, lines, because when you talk about the line, we are mainly concerned with the fault signal, actually, because if the line trips, how does the fault current and the line will change? That is what we talk about. Then again, the load, because you could have static load or you could have dynamic load as well. Because if I take the lighting load, right? So in case of lighting load, you don't have any rotating component, so that is as a static load. But if it is a motor load, then it will be a dynamic load. So all these components in a power network, they have their individual dynamic characteristics uh, against the disturbances here. And this dynamic representation of the components, they can be modeled. They can be modeled in terms of some equations, that is the differential equation. So it is something like saying differential equation of the components of the system will tell you how the time response will vary. That means how the generator is going to change its behavior, or turbine, or maybe even excitation system, the controller, or the controller, another one, governor. I mean, so how they are going to change, what will be the dynamic variation of the states for each of these components. They are actually a model in terms of differential equations, and they will tell you what will be the response in time domain here. Thus, time frame is important. That means whatever the kind of analysis which you want to perform, uh, in that case, what is your time duration interest, basically, whether you want your analysis just for very short duration, or you want your analysis for a comparatively longer duration, or maybe little bit more or a higher duration. So time frame is important, basically, because our power network, the system dynamics, it has a wide range of time frame. And then again, it is also important because you have your components and their entire integrated network. So for what purpose? What is your objective in the analysis? That is important here. If you want, let's say, if you want your system behavior for fault condition, let's say, or if you want your system behavior dynamic representation, let's say for small load changes, right? Or if you want your system response or system behavior just as a steady state, not much changes, not much perturbation in the system involved. So thus, uh, depending upon our objective involved in the analysis, you may have some level of simplification in the model development. So that means uh, these differential equations which describe the system behavior, they can be simplified. They can be simplified to represent the phenomena which you want to study. As I said, let's say you want to study the fault. Then if you want to have the fault analysis, then the generator model has to be detailed one, then the transform, because the fault current will flow from the generator to the transformer. And then the transformer model has to be more detailed, because transformer, the saturation part, right? Because the fault current will flow to the transformer, and thus it is very important that how well you are able to model the saturation effect of a transformer. Let's say that is for fault analysis. But if you want to perform some study for generator control, then transformer modeling is not very important. You don't need to have much detailed model of a transformer. I mean to say, considering the saturation effect and so on. So that means depending upon what kind of dynamic analysis you want to perform, so some level of simplification can be achieved. Yeah, all right. And then you have to know for what analysis your model is valid. This is important here. Because you you cannot use a steady state model for fault analysis. That is not possible, right? Because when you say steady state model, it is only for, it is for the system where the equations, the differential equations, they are at steady state quantity. There is no perturbation basically. So thus it is important, then you know what is the validity of your model that you have it for the analysis. In that respect, this slide now here it says uh, what is the dynamic behavior of the several range of the components that we have in our power system. And if you look at here, this starts from very low. In fact, micro range, microseconds here, right? Now, can you tell me what could be the situation, what could be the phenomena which the power system could be exposed? Power system could be exposed for the dynamic in this time range. Can you give some example? Yeah.
Power system that is,
Sorry.
if there's a fault, wouldn't it be quite quick, or if there's like a short circuit?
Short circuit fault. Okay. Any more? Let's see. You have a transmission line, right? You have transmission network, and let's say the overhead conductor is exposed to lightning surges, and these lightning surges, they are typically the amplitude of the time, actually, right? The amplitude of the signal of the lightning surges, they are in the range of few microseconds basically. And if your transmission line is exposed to a signal, lightning surge signal, which is of very short duration in the range of microseconds, right? So that is something where you have the system dynamics governed by lightning surges of microseconds. Then, as Ibrahim said, uh, if you consider the fault, for normally the fault, what we observe, because this is 50 hertz, right? 50 hertz means time duration will be, one cycle will be 20 millisecond, right? One cycle is 20 millisecond. So normally what we observe in a power network, uh, the temporary fault, right? I'm talking about the temporary fault here. Temporary fault could be of in the range something 60 millisecond or 80 millisecond, 100 millisecond, 120 millisecond, temporary fault. Temporary fault, for example, it could be, let's say that you have a branch, T branch, right? And because let's say the overhead line passes through the forest, and then it has the trees have grown up in the height, and then let's say that during the wind storms, one of the branch from the tree breaks, right? It breaks and then falls on the ground. And let's say that because of high loading, and then you have sagging of the conductor, and then during the fall of the tree branch, it just touches the conductor for a few milliseconds, right? So that is basically a temporary fault. It's not a permanent fault. And normally we observe in the power system, temporary fault could be of duration something 100 millisecond or 120 millisecond. So thus the system behavior, right, during the fault condition of temporary, right, temporary fault conditions, how does the system will behave? So this could be a phenomena related to the fault occurrence here, right? Then again, you can have, let's say, something like low frequency oscillations, right? So if you have a low frequency oscillations or rotor angle, so again, it could be a few runs, a few something for a few cycles, it can be also, right? That, but again, the rotor, because this refers to electromagnetic, right? So it could be just for very few, in fact, few cycles, something, but again related to the from the rotor angle side, it could be. And then related to this one, you have the electromechanical phenomena, that there it could be the rotor angle. And but you can see it has a wide range, because you have inter-area oscillations, and then even the local oscillations. And in most of the cases, the low frequency oscillations can persist for a longer duration, even after the disturbance, right? So if, let's say, the rotor angle oscillations is low damped, all right, it's not a good damp, so that means the oscillation will adjust for several seconds, and maybe maximum up to 1 minute, or it will adjust throughout. That is also possible. Then here, if you refer this one, another phenomena, and here it could be from few minutes or to several hours, but again, depending upon what you have. So, but can you give some example here which involves the thermodynamic phenomena, at least in context of electrical system? Yeah,
Thermodynamic phenomenon,
yeah,
like overheating or what? I don't.
yeah, it will be related to heating only, but how it is related to power system?
I'm not sure.
Yeah, yeah, just see, because this is the thermo means related to thermal, right? Heating, right? And most of the generators that you have in a power network, they are driven by steam turbine. Am I right? It is steam turbine or the gas turbine, right? Agreed or no? So,
Yeah.
so now, if it is a steam turbine, then you have to you have the boiler, you have the furnace, right? If it is a steam turbine, you have the boiler and the furnace. So in the boiler, you in fact in the furnace, you burn you have the combustion process, cool combustion process, right? And then you generate heat, and then in the boiler you convert the water into steam. That process takes place. So that all involves the thermodynamic phenomena, because it is again related to steam. In fact, the turbine, steam turbine here, and steam turbine is coupled to generator, electrical generator, right? So now just see the the dynamics of the turbine, and then because the input to the turbine is from the boiler, right? And then the boiler dynamics will depend upon how does the heat generation takes place, basically combustion process. And again, the combustion process can be much slower, right? And then the temperature buildup or the pressure buildup in the steam turbine, and then the dynamics of the turbine, basically, and then finally the electrical signal dynamics in the generator. They are all indifferent, right? And thus the thermodynamic phenomena, as in the case of a steam turbine, that could be from few or several minutes, even up to love. You can see, yeah, it can be for several hours. Because let's say you want to start your thermal power plant generator, basically, right? So what you will do, you will first start your combustion process in a furnace, then you will have certain amount of heat being developed. Let's say you have something 900 degrees centigrade developed in the furnace, and then you will have your water being converted into steam. And again, it should be at a much higher pressure. So again, you will have superheater in the boiler. So that process again, it takes time. So altogether, the phenomena which is involved in the power generation from the thermal power plant, basically, that is the long, much higher duration. So you can see here that our power network, it in fact exposed to a wide range of phenomena, which is had a wide range of time duration, basically, right? Starting from the lighting surges, that is much faster, and then again, the behavior what you observed in the furnace or the boiler, it is much slower, basically. Then again, if you talk about the generator behavior, it could be somewhere here. And if you talk about the generator behavior during the fault, then it would be somewhere here. And then again, the dynamics which is involved when there is just some lighting surges and so on. So it will be somewhere here. So thus the complete power network, it is exposed to wide different phenomena, and these phenomena, they have wide range of time duration to which our power network is exposed here, right? Anything on this? Okay. So next we have the what is the small signal stability for SMI based system. Yeah. Now, just to understand what is SMIB, consider this figure here, right? So it refers to single machine here, right? So you have one generator. It could be a one large generator, something 1000 MVA generator, yeah, right? And let's say that this generator had its own load or maybe some shunt admittance here. That is also possible. And this generator is connected through a transformer. It could be here. And then there is a substation, the bus here. And then it may have its own some load or maybe some compensator here. And then you have your line here. So what you can see here, there are two parallel lines here, parallel transmission lines, and then at the other end, again you have some certain admittance, and then connected to a large network. So that means a one generator, you have actually the connection of one generator through a line to a large power network, right? So you could have, let's say you want to understand how does this generator will behave if there is some disturbance on the generator side, or if there is some fault here uh, against the large network. This is what we want. So this machine is connected to an infinite bus here. So that means this is your infinite bus, a large network. And if what do you understand by when we say infinite bus? Mhm.
Yeah, kind of, yes. It's like a large network that's represented by one bus.
Yes. So when we say a large network, which is though, in fact, there is no infinite bus in our real system. All right, there is no infinite bus in the real system. Even though it may be very large, but it cannot be as infinite bus. As per the definition of infinite bus, it says that because this is your large network, right? You have the generation here, you have the load here in the large network. Whatever the changes you have in the generation side and whatever the changes you have in the load side. All right. If you have generation change, if you have load change, but the system quantity, the system variable, the voltage and frequency, they are as constant here, right? So if you have some power network, a large power network, wherein irrespective of generation change and the load change, voltage and frequency are maintained constant, then it is an infinite bus system. So, but do you think that it is possible that because whenever there is a generation change or the load change, there will be always change in the voltage and the frequency? Am I right? So can you have any large network where you have this two quantity constant? Yeah.
You mean the voltage and the frequency constant?
Yes.
In
Let's say,
real systems, no,
yeah,
but
yeah.
you can assume that they are.
In real system, it is not possible. Even though it can be very large network. Let's say something, you have a large network of something power capacity of 60,000 megawatt or 60 MVA or even uh, uh, half a million something, or right, or 90,000 MVA and so on. But it's still uh, uh, there will be some fluctuation in the voltage and the frequency whenever you have generation on the load change. But this is just theoretically we say that that is our infinite bus system, where you have, whenever there is a change in the generation and the load, we are able to maintain the voltage and frequency constant. So that means it is relatively a large size network uh, for which there is no change in the voltage and frequency here. So it is virtually there is no change here. And that is, we call it at constant voltage or constant frequency. That is your infinite bus system here, right? And thus the voltage quantity at the infinite bus system here, right? Yeah, we can say that will be, in fact, the voltage quantity which we have it here, the bus where you have the connection to the infinite bus system. Here we say that this quantity, the magnitude value is constant, and we take this angle as a reference quantity here. Right. So normally for an infinite bus system, the bus quantity, the bus voltage here, it will be always as this one, which we refer it here as a reference quantity here. And then from this layout, we can have a equivalent circuit here. So we can have generator and then all the impedances, what you have it here. Impedances or the admittance basically. We can obtain a equivalent system here, equivalent reactance here. And thus at this point, we have the generator voltage, and at this bus, you have your infinite bus here. Now, yeah, maybe you can say this quantity, it is either here or it may be at this bus. Doesn't matter. You just only take into account this impedance, nothing else. So we can also say infinite bus voltage here is over here. That is also there. Right. So that is the infinite bus representation in the equivalent circuit form here. Right. So maybe I can explain it. This is how we try to model them. So what you look at, this is infinite bus. Then your impedance here, the line impedance here, right? This one. So it can be something like this one. This is your line impedance, and then connected to the generator here. So this is your generator bus, which you have it here. This is your generator bus here, and then your generator part here. And now, because we want to analyze system behavior, and mainly we are interested to analyze the behavior of generator here, right, which is connected to the line to this network. So we have to consider all the modeling aspects of this generator here. And this generator, what you have it here, it is coupled to the prime mover, and this could be your turbine, right here, steam turbine or the hydro turbine here, right? And then again the steam inlet or the water inlet to the turbine, it is by through the valve or the gate control here. So, and the control of this valve or gate will be through the governor here, right? And how does the governor will control? That will be basically through a feedback of speed signal, right? Angular speed signal from the generator terminal. So there is a feedback here, right? Yeah, this way. Then again, the generator also has field circuit. So this is your field circuit here. This one. And this field circuit has to be excited here from a DC source. So there is an excitation system here. Right? This is your excitation system, which will provide the field current or the field voltage to the field circuit so that you are able to generate this much voltage at the generator terminal here. So this is one. So because we want this voltage, we want to control this voltage, and we want to control this frequency here. And thus from the generator terminal, you have this feedback. And then from the generator terminal here, right? What you find here, that through the excitation system, there is another feedback here. This one. And here you can see there is an automatic voltage regulator. We will discuss about this later on in the later topics. Here you give what will be the reference voltage. So that means you decide what should be the terminal voltage here. You decide. So you give your reference voltage here so that your actual voltage of the generator terminal is regulated. It is controlled here. Right. And thus this is your actual voltage here. And then the error signal will regulate and then through the excitation system, it will regulate the voltage. Then for the rotor angle stabilization point of view, we also have one more feedback that will be basically normally you can say omega, or it can be also delta, but to most of the cases we use omega signal. So because it is very difficult to measure the rotor angle, right? But with the PMO signal, you can measure what is the bus voltage. So it is possible, right? So we can use both delta or omega signal as a feedback signal to the stabilizer. This is your PSS, power system stabilizer, and then it gives a signal to the stabilizing signal to your AVR section here. So this is your AVR section. So you can see that the excitation system or the AVR, it has two feedback. One is the stabilizing signal. This is voltage stabilizing circuit signal, and this is your actual voltage. This is the actual voltage which you get it here. So overall, when you have to model, right? When you have to model the one generator, you take into account the differential equation of the generator, the prime mover, the governor, excitation system, and even the PSS here. So this completely represents one generator circuit or one generator system. So generator and along with the auxiliary devices, the controller part basically. Yeah. Right. Anything on this block diagram? This could be more simplified or maybe detailed one. What we have, if you remember, in the beginning of the lecture, I had discussed another block diagram where you have the generator, turbine, and all. Do you remember? I have shown two feedback loop for the one is through the governor and another is to the excitation system. Do you recall or no? It is the same thing, in fact, here. It is the same one here, right? It is the same one here. Yeah. So this one, what we have it here, the how we apply the modeling approach here, right? And what you can see, this is your source, genetic source here, right? And then you can say this could be the reactance of the generator. And then this could be again the reactance of the external circuit, basically. It could be transformer and then your line, and then your infinite bus system here. So you have the power flow. You have the power flow from the generator to this side of the circuit here. So this is the amount of the power flow from the generator side, and then to the load side or the infinite bus circuit side here. Now we write this equation here. This is the complex power, right? This is the complex power. That is this one here. And in fact, the power flow from this part to this part, what we can, in fact, the generator terminal, this one, the power flow from the generator terminal to the infinite bus circuit here. That will be basically the product of what is the voltage here and what is the voltage here, this one. And then sine of the angle. So if you remember, for the infinite bus, we have considered this is your voltage quantity, the voltage which is at the infinite bus here. It is this one. And angle we have considered your reference. And then the angle which you have it on the generator, it is delta here. And then these two reactances we have sum it here. So thus writing down in terms of active power and reactive power, it is this way. And we can in fact neglect the resistance here, and then in fact at a steady state point, actually Maybe I can switch to another one. I could have it another one more slide for you here. Can you see this slide?
Yeah.
Yeah. So let's just say I have this slide in discussion for later chapters, but I thought maybe I can have it. Now just see how we write the power. What is the relationship between the power and the torque here, right? Okay. This is power and this is torque. They are related by speed. Am I right? Now, when I have my generator, right, or the turbine running at steady state quantity, so in that case, it will be unity value. That means there is no speed deviation, right? There is no speed deviation generator and the turbine at steady state quantity. So thus, this angular speed, it is unity value. I'm talking about in terms of per unit, right? So it is this way. Then the mechanical power and the electrical power and the power which is at rated condition. What you get it here? It is same. So we can write in this way. And now this you can say this is your angular speed of the machine at rated condition. So it is this way. So thus all the three quantities, they are same. Now if in case you apply some disturbances in the power or mechanical power and thereby the torque, what you have it here, right? And same way the electrical power you have some, and then the electromagnetic torque which you have it here. So that means you have introduced some finite amount of change in the mechanical power and the torque and the electrical power and the torque here. Then what is the difference between the two power, mechanical power and the electrical power? So it is this one. Is finite change in the mechanical power and the difference in the electrical power. So thus we write in this way. And this can be further written down in this way here. Right? Because you will have, this was the original speed, rated speed. And then the, what is the is angular speed deviation. And then that will be, because this is power. So yeah, this is the power is omega times t. So this is omega times t here. So what is the change in the torque from the mechanical and the electrical side? It is this one. Then we can write in this way, and then we have some manipulation. We are doing some manipulation here. So approximately we can write in this way. So the change in the power, basically it will be this one here. Now, so from this relationship, we can have the generator model representation. So we can write in, or we can write this as 2H as this one, and difference of Tm minus Ta. So that is same as Pm minus C, because it is at rated condition, because your generator is running, and at rated condition or the nominal condition, you perturb it, you introduce some disturbances here, right? So thus you have this one. And this is how it is related the angle and the speed here. It is related this way. So thus the classical representation for the generator model, it is this way. So this is d by dt. What is the angular speed deviation here? And then again, what is the d angle by dt? So what is the rate of change of angle here, rotor angle? So thus the classical generator model can be as two differential equation here. One is this one, another. So this is in terms of speed deviation, and this is in terms of rotor angle here, right? So classical generator model can be can be represented by two differential equation here, right? And this equation we can have it because the generator will be connected to the load, right? And this is the electrical power, but the power flow to the load, right? This can be again categorized, right? So just say you will have static load, and then you have a dynamic load, right? And if it is a static load, then the those load we call them as frequency insensitive load change, right? And then those load which are dynamic load, they are referred as frequency sensitive load. So thus the load perturbation, the load disturbances can be resolved into two parts. One is insensitive, frequency insensitive, and frequency sensitive here, right? Do you understand by this?
So you mean if you have a motor, then the speed is going to be sensitive to the frequency, right? So any change in that is
Yes.
going to be affected by the frequency, or it's going
Yeah.
to affect the frequency also?
No. Okay. And then just go
I'm
ahead.
not
What?
sure.
Okay.
Yeah, is it affected by the frequency or it affects the frequency?
No. Just here. Whenever you have a change in the dial PG, and then again you have some deviation in the dial PL, right? Now this part, this is the change in the generation side, and this is the change in the load side, right? Now, if there is a mismatch, right? There is a mismatch between the generation side and the load side. So what will happen? Frequency is going to change, right? Now let's say for your frequency change has it is something, let's say 49 here. Yeah, let me write. In fact, sorry, this is okay. Let me. This is 49.5 hertz, right? This is 49.5 hertz here. Now with the change in the frequency of 49.5 hertz, do you think the power drawn by lighting load will change? The power drawn by lighting load at 50 hertz and the power drawn by lighting load at 49.5 hertz, do you think it will be changed by the lighting load?
No, as long as the voltage is stable, it should not change.
It should not change. So that means the lighting load, it is frequency insensitive. That means the power drawn by the lighting load does not change if the frequency has changed, right? Just see, I say because this is 49.5, so that means the load has increased. Am I right? Load has increased, so the
Yeah.
frequency drops. Now, if it is a lighting load, then the drop, because of the drop in the frequency, the power drawn by the lighting load has not reduced. Am I right? Power drawn by the lighting load has not reduced, or it has not increased basically, right? Here, this one. But if you say frequency sensitive load, it means that here, if the frequency drops takes place, then the power drawn by the load will also reduce. Okay, the power drawn by the load will reduce. And if you remember, I'm not sure, if you take the induction motor, and this is the torque shift characteristic here for the induction motor, and this is at synchronous speed here, this one, right? And let's say this is your operating point here, right? Then, and here this is your torque, right? And if the frequency drops, right? If the frequency drops takes place, then the torque, what you have it, the power drawn by the machine, that is going to change here. So that means what will happen? What will happen that Because of the drop in the frequency, the power drawn by the load, the motor has shunt. But in what direction it will change? Can you guess?
I'm guessing it will decrease based on this one, right?
No, this
8.
is synchronous speed here. That
No,
means
but
this will correspond to 50 hertz here, right? If the frequency has, because let's say this was the initial operating point here, right?
uh-huh.
So if the
Wait, that
frequency
means it will
reduce,
increase. Yeah, it will
it will
increase.
go this way. That means
Yeah.
the there will be shift in the characteristic. That's why it is. Let's say if the frequency had reduced, the operating point will become this one, right? So that means there is a shift in the characteristic for the motor. So what is happening here? You see, effective load has increased. Effective load has increased, but because of the drop in the frequency, the in fact the torque of the motor has changed here, right? That means the it, and this is developed torque, right? This is developed torque. The developed torque of the motor has changed. So what does this mean? This is basically, this change in the torque is basically something like the motor is having a positive effect of generation in the system. Positive effect means, because you see, if the load has increased, then the entire power has to be made from source, from a generator, right? Am I right? But from the motor side, what happened? If the frequency has reduced, the torque has changed. The electromagnetic torque has changed. And so thus, this change in the torque is having a positive change in the power output, a positive change in the power output in the system. That is from the motor behavior basically. So this is having a positive effect. And thus, in that case, this positive effect is applied on generator here. And thus for the short duration, there is a positive effect, and then the frequency may not dip further. It may not dip further. So that means the initial surge, initial increase of the power or the developed torque which you have it in the system, it is provided by the motor here. And this is affecting
Wait,
a
I don't understand. When the developed torque increases, doesn't that mean you're putting more load or demand on the
no load.
generator?
No, just here. I'm saying this is the combined load. This is the combined load. So it is possible that your lighting load has increased. Your lighting load has increased, but the motor load is constant. Right? Let's say this is your total load, and I said total load is increased. So it is possible that your lighting load has increased, but the motor load is constant. Am I right?
Okay, yeah.
Yeah. So now if with this situation, with the load increase, the power drawn by the, because lighting load, the power drawn, or that means because lighting load cannot generate or consume, actually it cannot. So that means the power drawn by the lighting load remains constant even if the frequency has increased or decreased. It is insensitive. Am I right? Okay.
Yeah.
So in that case, if the load has increased, then the power has to be made from it has to be made by generator size. Am I right? It has to be made by generator side. Okay.
Yeah.
But if it is a motor load, right? If it is a motor load, then because of the drop in the frequency, the torque has changed. There is a torque increase. In fact, it is a positive torque basically, right? So that your mechanical load on the motor is constant. Okay. But the torque developed by the machine, it is now positive. So this positive torque, it is a positive power in the system. It is a
Wouldn't that
positive.
just increase the speed of your motor? Because before you
No,
mentioned the torque and speed
no.
characteristics.
Yeah, but it is actually uh, speed has reduced. The frequency has
No,
reduced.
I'm not saying the speed of the generator. I'm saying the speed of the motor.
Yeah, I'm talking about the motor only here. This is the torque characteristic of motor. So because
Okay.
this corresponds to the synchronous speed, and this
Mhm.
is, let's say it is something around 1460 RPM, right?
Okay.
And
Yeah.
because but here it frequency has reduced, so it the characteristic has moved to this one here now. So this
Yeah.
is
So it's
a
going to be higher
positive.
speed, right?
No, this one it will be lower speed basically,
Okay.
because this is synchronous speed 1500 RPM and this is
Uh-huh.
0 RPM here. So it is
Okay.
moving this side. So this is higher torque. So that means
Uh-huh.
higher torque is developed. So this higher torque, that means positive torque in the system, right? So that means the motor is providing a positive torque, but it should have been from the generator side basically. Am I right? Agreed? It is the motor which is providing a positive torque, which
Yeah, but
should
the
have
motor is providing a positive torque to what?
to the
To the
system, to your system,
to
to
the
our network,
system.
to our network. It is
Okay,
actually.
and what does that torque translate to in terms of current and voltage?
Yeah. So that means that way the initially when the disturbance took place, there is no need to have the all the power to be made by generator. All right, the moment disturbance takes place, there is no need that the power has to be made by generator, because of this positive torque can also be have an impact here, and thereby it can minimize the frequency deviation. Let's, for example, let me I say this way. This was 50 hertz, right? And let's say the frequency dips here, right? And if in case there is a motor load here, then this the initial, this is a positive torque, and thus it will try to minimize the dip in the frequency here. So that means it is having a positive impact, positive torque impact in the system, and thereby try to compensate the drop in the frequency here. It is happening this way, and thus these are actually frequency sensitive load here.
So that is useful for the system, right?
Yeah, that is useful for the system. You are right, because it means that if you
Oh,
do not have the motor load, if you do not have motor load, then if you just have lighting load, if you just have lighting load, then let's say for the 50 megawatt load change, 50 megawatt lighting load and the 50 megawatt composite load, if you just have only lighting load, the drop in the frequency will be much more. But if you have a composite load, combination of the two, right, lighting and the motor load, then the same for the change, for the same change, 50 megawatt change, then the drop in the frequency could be less. This is what is affecting the system dynamic behavior. Yeah, yes. Right. So if you, that means it is the motor is having a positive impact. It is having a positive impact in the system stability. It is this way, and thus it is trying to minimize the frequency deviation. This is what it refers here, and that's why we call this term. This is the load damping constant here, and this is useful. So that means your power network should have this kind of load. Your motor load should always be there in your system. Otherwise, if you don't have any motor load, the frequency will dip much more if you don't have it, right? Okay, agreed
yeah,
or
this
not?
is the first time I hear about this. So
Okay, okay, okay. Yeah, this is what it, and that's why it is changed. What is the percentage change in the load to the percentage change in the frequency? Yeah, load damping constant, we call it as. This is, and that's why, let me tell you, just say, we talk about the microgrid and we talk about the conventional power system, right? In the, if you have a microgrid, so let's say that you just have residential load basically, right? Residential load in a microgrid. Now residential load in a microgrid will not have motor basically, right? You will have just lighting load only. Am I right? So now if you in a microgrid, change in the load affecting the frequency deviation is much more. And if you consider a conventional power system which is interconnected, then the change in the load affecting the frequency, it is much less severe. It is much less severe. And thus we say the control of a frequency in a microgrid is much more difficult than the control of a frequency in your conventional power system, because conventional power system will have some amount of uh, machine motor load, and thus it will have a few dynamics involved here, right? Is it agreed?
Yeah,
Okay,
just
we will
kind of
have some break.
understand
We
the
will
basic idea.
okay. We will have some break and then think over it. Okay, fine, fine. We'll have some break. How much? 2 minutes?
Can we have like 5 minutes? Two
Okay,
minutes
fine.
is
Okay,
too
5 minutes.
small.
Okay, 5 minutes. Okay. So now, do you have any confusion or anything is clear? What we discussed that how the presence of motor load is helpful in maintaining the frequency deviation. Yeah. So, and thus the load damping constant, we define it as what is the change in the load to the change in the frequency here. And then from the previous relationship, this one, if you remember, the rate of change of deviation in the angular speed here, right? So this rate of change we can replace by a Laplace transform. Do you remember last semester we have done this way? Because this is the differential equation representation, right?
Yeah, I remember this
Yeah,
equation. We had it last
yeah.
semester.
So, and here this is your S transform. So we can write in this way. And then here we have represented what is the change in the power from the two sides. And now this one, this quantity, we have represented from here, this one. Right, so we have this manipulation. And then we can say that the difference of the two power. So that means this power is from your turbine side and this power is your basically the load, the electrical load, which is connected to generator. It is this one here, right? And the difference, so difference in the turbine power and the electrical power, it is basically the generator output basically. This difference will cause, it will result to deviation in the angular speed depending upon this quantity. and it is this one. So here you have 2 times the inertia constant, that is your M and S, and this is your D here, the load damping constant. It is this one. So this is how we represent a classical model of a generator by 2 differential equations, and this is the most simplest model for generator dynamics, and we use it. We use this generator model whenever you have to analyze the frequency deviation. So because this is the output, so if you want to analyze the frequency deviation of the generator, then it will be based on this error and the system parameter here. So what is the inertia constant? What is the load damping constant here, right? Is it okay? So with respect to that, we have this one now. So maybe I continue here. So what we have written down, it is this one. So the torque, the electromagnetic torque or the power or the turbine power, we write in this way. And this quantity is your P max here, right? Because this is the amplitude here, this is the amplitude. And then we can draw. This is your P, this is your P, or maybe the torque, what we write, and on this axis, it is your angle here, this one. And this is this quantity is a sinusoidally variant. So we have this one. So thus at 90 degree, when the angle delta, when your angle delta is 90 degree, then you get the PE or the TE will be maximum, and it is this quantity. So it is this one. So you get a P max maximum when angle delta is 90 degree. And if in case your operating point for the generator angle, it is something this one. So this is your initial operating point. So what you find here that at the steady state point, the electrical power and the mechanical power, just see, remember that this is mechanical power, this is constant, right? This is represented, the mechanical power is represented by a constant line here. But this one, this characteristic is represented by electrical power here, this one. So in fact, that means any point on this characteristic, it is actually electrical power here, this one, right? This one. Now, if I ask you, you apply a change in the turbine power, how you will apply it? What will be the change in the characteristic? Can anybody say? Change the turbine power.
Isn't it going to increase the power like this?
Yeah,
so you move up
okay, we move up. So
yeah.
This is the initial point, so it means you move up, right? And then where it will intersect here. So it is
Yeah, somewhere here.
here. Yeah. So this is your. So that means for the increase in the turbine power, let's say suddenly, let's say here, suddenly you have applied a gate change in the power, right? You have suddenly increased the opening here, right? You have suddenly increased the opening here. Then what will happen? Then that means the turbine power will increase. But again, just assume, because even if you increase the turbine power suddenly, because there will be again some time lag involved, all right? But here on the x-axis, it is not the time, but it is the angle here, right? So just in that, let's say that it is a step change here, right? And then on the PE curve, what you have, it is this intersection. So if you increase the turbine power, you have an increase in the angle here. Okay, so that means the now the next operating point is this one. So this the new operating point will be this one here. Now, so let us, this was the equation here what you have, and let us linearize it this one, initial operating point. So that means we substitute delta is equal to steady state value, initial angle is this one. Now from the same relationship what we had earlier, uh, I mean from here, just see, it is the same form of the relationship here, right? 2hs dial omega and then this term. It is the same thing here. But only thing is that instead of D, the notation what we have it here, it is KD. It is the same, right? And this is TM, what you have it here. And this is PL, that is electrical load. It is this one, this quantity. It is the same. Then 2hs, it is this one. And S dial omega, this is this one. Because this is P, that means it is actually differential quantity. What we have said, it is P is X. In fact, I can say it as this is actually D by dt term here. This one, this quantity. So that's, and then again from the previous relationship, if you go back, what we have it, this one, this quantity, right? So it is this one. This is d delta by dt, and then we multiply it here, omega naught, and into del omega r. So it is this one here, right? So this is how we have represented here, written down the manipulated equation. And next, what is change in the torque, electromagnetic torque here? This we write down. Now just see. This is PE, right? And the same as TE, right? Now, when you have cause, when you have a some change, right? When you have a some change here, right? Then what is the differential change of the torque with respect to angle? So that means this one, right? Because this is PET. So what is the partial differentiation of torque with respect to angle? And then we have written down this way. So you, that means this is the torque. You partial differentiate this quantity. So it is E prime EB by XT, and then sine. What you have it here, it becomes cos. And since we are equating at this one, so cos of delta naught and then del delta. It is this one here. So this, what is the change? Finite change in the torque, we write it this way. And this quantity, we will refer it as synchronizing torque here. That means it is this coefficient which will be responsible to synchronize the system, right? The torque and the angle basically. And we will use these terms very often, right? And then that we call it as synchronizing torque. And this, what we have it here. So if we write it from this term, this, it is this way. And then again from here we can write PMF. So synchronizing torque, what you have it here, synchronizing torque coefficient, it is this one. And thus, instead of writing this now, we have represented it here this way. So it is the same expression, but we are now we are writing at some small change here, right? So change in the torque, mechanical torque, and the electrical torque here, delta T. So it is this one. So this is actually Ks. Ks is this term. Then to del delta. So we have written this, and we already have Kd into del omega. It is this one. and then change in the angle we have here. So finite change in the angle and then speed here. Right. So this is the procedure. This is the we have the nonlinear equation here, and this is the procedure to linearize. That means to linearize, what you do, you just do the partial differentiation. You do the partial differentiation around the steady state point. This one. This is the procedure to linearize any equation here. Right. Anything up to this? Okay. Then now from the previous two differential equation here, right? Previous these two differential equation, we write down in a vector form. This is the state vector form because this is d by dt here. So d by dt. So it is del omega and del delta here. Right. So it is the same thing what we have it here. Del. Because if you remember this quantity, it is d by dt. So we represent this. Now this is what we call it as state vector. This is your state vector here. Two quantity. There are two state vectors here. And then this part, whatever the quantities which you have it here. Now just see, this is x dot. This is x dot, and this is also x dot. And then when you write it as a form in the form of, if you remember, earlier we have written it as x dot equal to a x plus b u. So this is x dot, and this is a matrix. So this is a matrix here, and then x, it is this one, plus b. So this is b and u. This is the u here. Okay. So what is b matrix now? Can anybody comment?
Okay, 1 over 2h and 0.
Yeah. So that means you are representing in the model the turbine power. All right. The turbine power as the input here. Okay. Because this is the B matrix, and this is the turbine power you are representing as the input to the system. So now we will write. So in a we will show the in a block diagram here. So just say we have two states here, right? And what you find it here, in fact, if you start from here, this is rate of change of speed. So 1 by 2h del t minus this term, right? This is te, yeah, this one, and minus this term. So with that, this is del tm, this is the input, right? And then del te minus. If you refer from the previous, del te, this is minus here. But what is te? It is ks times del delta. But del delta is the state variable here. So it will be to the feedback. So this is your feedback. So you get it here. Ks times del delta, that is your del te. So you draw this line. This is the signal path here. Then this difference 1 by 2hs, this one, right? And then the, if you refer, maybe I go back from this one, if you refer here, this one, the difference of the two power, this is the inertia and then speed here, right? But here, if you look at, there is small difference. In fact, this one, because this is 1 by 2hs, we have written it in the feedback here because this is kd, right? Kd times del omega, right? It is here. So because if you look here from the previous here, this one, kd times del omega, and then divided by 2h here, this quantity. So we have it here. So it is multiplied and then feedback here. So this, and then you get one state variable omega here, and then from the previous this one, this is rate of change of, so it is this quantity. So from here we just integrate it. So when you integrate del omega and multiply by this, you get it del delta. So thus from the two equations, two differential equations, we have drawn this complete block diagram here, right? Is it okay? Yes, Usagi? Claire, are you here?
Yeah.
Okay,
Okay.
okay,
Yeah, I'm here as well.
okay. Any doubt here, Meenakshi?
Any what?
No. Any doubt here?
I'm just trying to follow.
Okay. All right. So this is the synchronizing torque coefficient, damping torque coefficient, inertia, speed deviation, rotor angle deviation, Laplace transform, and the rated speed. This one. Yeah, here it is because the book I had it from Kundur, so they have it at 60 hertz, but this can be at 50 hertz, so it will be how much? Yeah, at 50 hertz it
You
will
mean
be, yeah,
to
omega naught.
IF? It's
Omega naught will be equal to
314.
314, right?
Yeah.
314 here, radian per second, right? So then we write down del delta here in this way, right? And we write down this way. So this is actually what we are trying to analyze. This is the output quantity variable. So if I say, for example, let's say that suddenly you have applied a step change in the torque here, right? The mechanical torque. Then how does delta will they change? How does the rotor angle will change? We want to analyze this. And what we obtain, it is this one, rotor angle deviation here. And it is given by this number, right? So now this equation can be compared with the second order response. So this is the characteristic equation we write down for a second order response, second order system. Now, what is the order of the system here?
Isn't this the second order?
Yeah, it is 2 by 2. The matrix
yeah,
is
2 by
2 by 2. So it is a second
Ah.
order. So we are comparing the dynamic response of the angle with the second order characteristic equation. This is second order because the highest power of the complex variable, S is complex variable, Laplace operator. The highest power of the complex variable is 2. So it is a second order model. And remember the characteristic equation, it is to be equated with 0. And from this, I'm not sure, maybe in your course, advanced control you have, right? Advanced control. Maybe there you will have some discussion about the characteristic equation and then referring it is in this form. Maybe in the advanced control course which you
Maybe.
have.
We didn't reach that yet, but maybe.
Okay, but it will be, I think it will be. So this second order we can write in this way actually, right? So it is s squared twice of zeta omega and ns and omega. So this is in general we write it here with the damping ratio, varying from 0 to 1, right? So this is damping ratio or the damping factor. So now this quantity we compare here. And then again with this quantity we compare here, because when you look at here, this is S, this is S here. So what is omega? This is omega n square. Remember, omega n refers to undamped natural frequency. That means it is the natural frequency of the system which is undamped. there is no damping. All right, so at what frequency, at what natural frequency, the system will oscillate if there is some disturbances here. So at what frequency the rotor angle will oscillate when you have some disturbance applied here. This is what it refers to. So what is, when you compare this quantity with this one, right? So what you get? It is omega n is equal to under root of ks omega naught divided by 2i. So this is in radian per second. I have just compared it here, nothing else, right? And then when you look at now you compare this term, I mean this this value, twice of zeta omega n, and substitute omega n over here, and then equate it with this quantity, this one. Then you will get, and then you can determine what is zeta. This is damping ratio. So thus the system response, the variation of the rotor angle is natural frequency, and the damping ratio, it is given by this quantity. Yeah. Okay. Thus from the previous relationship we had this one, and it is the same way. So the second order linear system, we have this undamped natural frequency, it is this, damping ratio, it is this. Now from the characteristic equation which we have represented here, we get two roots here, and this can be represented. That means it will have some real part, some imaginary part here, right? So that means the response will be associated with the damping and as well as some oscillation, and thus the damp frequency response, it is given by this one, omega d. So this omega d refers to damp frequency of oscillation, right? So what does this mean? Let's say this one, this one. You have applied some disturbance, right? You have applied some, let's say, you had applied some step disturbance here. Then how does the angle, this angle will change? So if you have applied some disturbance, then it is possible. Let's say this was the initial steady state point, right, of angle, right? It was this one. Then following the disturbance, angle can change this way, this. So what you find here, that rotor angle will have few oscillation, and then it will settle down. Yeah, it will settle down. Then again, it is also possible that the rotor angle will have more oscillation. It will have more oscillation, and it will settle down later on. This is another case. Then maybe I could say this way. If you have, let's say, good response, right? Let's say, because this is a damp response. So let's say your response is something like this one. So your response will have only little small amplitude oscillation and then settles down quickly. So depending upon what is the damping ratio, what we have it, because this is a damped oscillation, and what is the damping ratio, this quantity which we have it previously, this one. So depending upon the value of damping ratio, the rotor angle will oscillate or settle down depending upon that. So what do you understand? Now, if I say synchronizing torque, right? What we have it here, synchronizing torque is this one. If the synchronizing torque reduces, that means decrease. How it will decrease? Let's say you have more reactance. You have high reactance of the line, right? or maybe you have increase in the because this is cos of delta naught. So if you have increased value of delta naught, that means cos of delta naught will be reduced, and thus this term will be reduced, right? Am I right or no? Agreed?
Yeah.
Yeah. So in that case, if the synchronizing torque reduces, then what about the natural frequency? Natural frequency is this one. So if this term reduces, that means the natural frequency will also reduce. It will reduce. And then if you look at damping ratio, if synchronizing torque reduces, then the damping ratio will increase. Damping ratio will increase, right? And then oscillation, damp oscillation will also, what you find it here, because this has increased. If this has increased, that means damp oscillation will reduce. Agreed? Agreed or no?
Yeah. Yeah.
Okay. Now, if you remember, Ibrahim, maybe last semester or maybe in the beginning of this lecture, you have talked about that if you have low resistive line and highly inductive line. Do you remember? If you have
I
high,
remember. Yeah. Yeah.
if
I
you
asked
have
the question
high,
about it.
yeah. If you have highly inductive line, right? Because the long transmission line will be highly inductive, but the line which you have it in the distribution network, it is mostly resistive because the distance is small, right? Agreed?
Yeah.
Yeah. So if you have highly inductive line, mostly for the long transmission lines, then natural frequency reduce, but the damping ratio is better. If you remember, I said that if you have line highly inductive, more inductive line, then the damping, the response will, that means stability will be more, right? Stability in terms of rotor angle variation. So it is because if you have higher damping ratio, so it is much more damped response. It is much more damped response here. So, but if we have a resistive line, that because when we say resistive line means we say weakly connected. All right, resistance is more weakly connected, and if it is a weakly connected, that's what it refers. The damping ratio will be poorer, right? And if you have highly inductive line, it means good damping ratio, and again the damp response. That means rotor angle will settle down quickly, right? So that's what we say, good damping. And if it is a highly inductive line, we say strong grid. Do you remember we said the word strong grid and the weak grid?
Uh-huh.
Yeah,
I know
it is
that resistance is affects damping. Yeah, that I know about.
yeah, this is the same thing. Yeah, this is the same
Yeah.
thing. Yeah. If you have highly inductive line, then your synchronizing torque is reduced. If the synchronizing torque is reduced, you have more damping ratio, and then again damping frequency. That means the response will the oscillation will also be lesser. It will be lesser. It will be damped response, damped oscillation. This is and that's why we say it as, if the inductive is more, we call it as strong grid, and if it is a resistive line, then we call it as weak grid. So this is what it refers to here, right? And then if you, let's say, increase in the damping torque, if you remember, we had this damping torque kd, which you have it from your load side, right?
This is due to the motors.
Yeah, from the motor side, how it
Okay.
affects. So with this one, there is, because natural frequency, it is independent when you look at because you don't have any term kd here. All right, kd, there is no kd. But if you look at damping ratio, higher the damping ratio, this kd, higher will be the damping ratio. Am I right? So if I say higher kd, that means higher damping ratio, and then your damping response, damping frequency is also reduced, and thus And this damping, what you have it, load damping, you will get it from your dynamic load, motor load. So if you have more motor load comparatively, then it will provide you more damping here. It will provide you better damping here, right? And then again, you look at inertia, because inertia you get it from a large generator, right? Steam generator, hydro generator. You don't get inertia from a inverter based renewable, right? Let's say the PV system, or even if it is a full converter wind turbine system, right? So you don't get inertia out of those renewable resources. But if you have a high inertia, mostly from your large generators, then your natural frequency reduces, because when you go back here, inertia is increased, and then the natural frequency goes down. Then the damping ratio, when you look at this is inertia, as you increase, so your damping ratio reduces. But here you just say damping ratio becomes poorer, what it refers here, 2H here. But and again, damp frequency also produces here, right? But again, we will, because this is just for a system, right? This is what we are discussing about the system behavior. We are not discussing about the how does the controller really have influence. We are not discussing that part here, because your excitation system, how it is going to affect the damping ratio, how it is going to affect your frequency, that part we are not discussing. We are only discussing what is the system, that means the generator basically, right? The load, because this you get it from the generator, this you get it from your load, and this you get again from your generator here. So how does the system parameter influence the behavior, influence the rotor angle behavior characteristic? This is what we are discussing in this slide here, right? Anything here?
Hello.
Yes, yes.
From what you have explained thus far, for the mathematical expression with respect to the inertia and the damped frequency, we discovered that you said when the inertia increases, the damping ratio decreases.
This is what we understand here. Yeah.
Yes. Now, going to the damped frequency, if the damping ratio decreases, the damped frequency is supposed to increase with the mathematical expression.
Okay.
Because if S squared damping ratio decreases, it means the value here will increase.
This difference.
Yes, yes, it will increase if this decreases, if the damping ratio decreases.
Okay. If I take, for example, damping ratio 0.3, right? And then 1 minus 0.3, so under root of 0.7, right? Under root of 0.7 multiplied by omega n. This is one case, right? And if I say this is something 0.1, so 0.1 whole square, so 1 minus this and under root of this. Just check it how it goes.
Okay.
Just check it how it goes. Yeah, just take some mathematical example. Just take it 0.1 and 0.3, right? And then see how it goes. Yeah. Okay.
Okay, go ahead.
But just wait, what you have referred. Okay, right, fine. Okay. Yeah, you can take this example, but what I understand, because this is square, right? And square of 0.1 and square of 0.3, and then under root of it actually. 1 minus the difference and then under root actually. So how it goes? So maybe I will check it again. Okay, I will check it how it goes. Okay. Right. Yeah, you have raised this point, but when I look at natural frequency, So I have H increase, so it goes down. So this is okay. This is okay, right? This is also right. But yeah, that's fine. But you talk about this one. Okay, we can take the example 0.1 and 0.3 and then check how it goes. Okay, that's okay, fine. Well, okay, then maybe we stop here. I think this because this will take some time. I think because I have. Yeah. Okay. I will. It will take some time. Okay, then we'll stop here. So yeah, one more point actually I wanted to discuss. What should be the what should be the this one? What should be the date for submission? Yeah, I think I have uploaded exercise 1. All right, and then add what that you want.
We can put it together with the other date, with the other assignment.
Okay, so all right, then okay, this is just then tomorrow we finalize. Okay, you give you have your think and then we decide tomorrow finally. Okay, agreed.
Okay.
Okay, and then
Yeah.
okay, then I stop here.